right. So my name is Zach Shwirep-Conti, and I'm a research associate at the Alan Turing Institute here in London. And I would also like to introduce my colleagues and co-organizers of the seminar series. So there's Andrea Pizzaperato, who is an assistant professor or a visiting professor at the University of Bath, and David Masagur, who is a PhD enrichment student here at the Alan Turing. So for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. On a side note, if you're interested in sharing your work on this topic of physics-enhanced machine learning or physical-informed machine learning, please feel free to get in touch with us, and we'd be happy to find a slot that works for you. As for the format of this seminar, our speaker today will speak for around 45 minutes, followed by a Q&A, as we always do. So without further ado, I'll ask my colleague, David, to introduce our speaker for today. And with that, I thank you all. David, you're on mute.
Good point. Hello, everyone. It's good to see you again. I would like you to introduce Arka. He's a final year PhD student at the Computer Science Department of the Virginia Tech, and currently advised by Dr. Anu Karpatny. Prior to joining Virginia Tech for his PhD, he received his bachelor's degree in electronics and communication engineering from Jadavpur University in India in 2019. And his current research is geared towards the development of next generation artificial intelligence solutions for scientific applications with the ultimate goal of accelerating scientific discovery. Specifically, his research aims at infusing underlying scientific laws and has experience with deep learning models to improve their overall generalizability and interpretability. He has worked on numerous interdisciplinary projects and has experience working on a diverse range of problems from lake modeling, climate science, solving partial differential equations to cellular biology. Arka, thank you very much for accepting to present today, and the floor is yours.
Yeah, thank you so much, David, for the introduction. Excuse me. Yeah, and thank you so much for inviting me here. I'm really happy to be here to share my work with everyone, and looking forward to some interesting discussions. I think we can also ask questions if you want. We can also pause in between and ask questions at some parts of the talk so that it's more interactive, perhaps. So I'll pause at some times and see if anyone has questions. So my talk today is going to be on like a small portion of my research. So we were working with uncertainty quantification with physics-informed machine learning. So that's going to be the primary motivation of this talk, or the scope of this talk. So let's begin with it. Yeah, so I think everyone here is probably very familiar with this idea about physics-informed machine learning. But if someone is new today, so let me just briefly try to introduce what this idea about physics-informed machine learning is, right? So conventional machine learning is usually trying to learn a mapping from this input to the output space, right? And that too blindly. Like, for example, if you're using neural networks, which are known to be universal approximators, it can approximate any function from this input to the output space, right? So we do not have any control about the form of this function, right? But for different scientific applications, so without just wanting to map directly the inputs to the outputs, we are also sometimes interested in ensuring that these predictions obey some scientific laws or scientific knowledge, right? So what we usually want to do is when we are mapping from this input to the output space, like a standard deep learning model would just map to an unconstrained space of output. Say if you're mapping between two vector spaces, it could map to the entire vector space. But what we are usually interested in for scientific applications is that we are interested in mapping the outputs to a very constrained, to a physically constrained space of outputs, right? Where these physics principles hold, right? Or are satisfied. So examples of these physics principles may be first principle conservation laws, like say conservation of energy, conservation of momentum, other laws or even sometimes it can be complex differential equations, right, which you want to satisfy. So you need to ensure that your prediction satisfies some differential equations and stuff like that, right? So that's the overall motivation about this physics informed machine learning. Uh, some of the recent success in physics informed machine learning, I think recently this physics informed machine learning is gaining a lot of traction. And some of the areas where it got success is, say, solving Navier-Stokes. So given the initial vorticity field, can you predict how the fluid would behave, right? How can you solve this Navier-Stokes to predict how the fluid behaves at different times, right? Even in turbulent conditions, we are able to predict. The other applications are in climate science, like lake modeling, methane emission, and stuff like that. So there's been a lot of work in that domain. The other domain, physics information learning, has gained a lot of success is physics simulations. So we are now able to generate like very complex physics simulations uh, to a very high fidelity, that these physics principles are satisfied, and how these particles, individual particles behave are very well formulated with these new new neural networks. So I think recently we have gained a lot of success in physics informed machine learning. What my talk is mostly going to focus on is uncertainty quantification. So in the first part of this talk, I'm going to focus on a special case of uncertainty, a special case of physics constraints which we looked at, and that was monotonicity constraints. And we looked at from a specific application point of view. So I'll go into what we are trying to do. So this was done in collaboration with other folks from Virginia Tech, as well as the United States Geological Survey. So before we go dive into what the problem was, let's try to define what is uncertainty quantification, right? So so sometimes rather than, so a standard neural network would just estimate the mean, right, of these predictions. But sometimes we are interested in more than point estimates. So sometimes we want to generate a distribution on the predictions rather than just being satisfied with these point estimates, right? So for a regression point of view, it would be, we want to predict the variance along with the output mean, right? And assuming the distribution is Gaussian, if you have some other distribution, other parametric distribution, you can try to predict the parameters of that distribution, right? From a classification point of view, we would like to predict the confidence scores along with the output labels, right? So rather than just saying the output belongs to a certain class, we want to say we are 70% confident that the output belongs to the certain class. And why is this important? This is usually very important in, excuse me. This is sometimes very important in scientific applications where you want to ensure trust in your predictions, right? Say you are predicting some quantity which is going to be used by some other person to operate something. So you need to know what is the confidence of your predictions, right? How likely that phenomena is going to happen, or how likely the output predictions belongs to a certain range. So that is very important for certain problems, especially in science or engineering. So so the first problem we looked at was the special monotonicity constraint, which naturally appears in this problem of lake temperature modeling. And the motivation, so this lake temperature modeling is about trying to model the depth, trying to model the water temperature of a lake at a certain point. And why is that important, right? So the water temperature has been shown to be important to predict the growth and the survival of fishes, right? Fishes cannot survive in a certain range of temperatures, and certain species cannot survive at certain temperatures, and so on. There are also these harmful algal blooms which show up on these lakes. So if the water temperature is too high, then it can have these uh, algal blooms. And this is usually lakes are fresh water. So a lot of these drinking water power plants are get their waters from these freshwater lakes. So if you have these harmful algal blooms, you cannot basically get the fresh water from these lakes, right, for these plants. The other thing is predicting the water quality. The water quality, like the amount of oxygen in this water and amount of phosphorus, chlorophyll, and stuff like that, also depends on the water temperature a lot. So understanding. So if we have a very good model for this water temperature, it helps really for a large variety of problem in this ecosystem, in this water ecosystem. So so how do we predict the water temperature, right? So we usually have these meteorological stations which measure some some features which are like say short wave radiation going into the lake, long wave radiation, what is the air temperature at the surface of the lake, the relative humidity, the wind speed, precipitation, and stuff like that. And what we want to predict is that at a certain point in the lake, say the deepest point, we want to model this 1D sequence in depth, right? So how does the water temperature vary with the depth of the lake, right? And we also want to predict for every single day, right? What is the water temperature? How is it going to vary every single day? So it's basically a 2D sequence. The one is a sequence in time. The other is going to be a sequence in depth, right? So we have two different time sequences. No, yeah. So what are the physics principles we know that affects water temperature, right? So the first one is on the left, is the relationship between density and temperature. So as we know that the density of the water is maximum at 4 degrees Celsius. And if you go to the ice, like if you decrease the water temperature, the density would decrease. And if you also increase the water temperature beyond 4 degrees Celsius, the density is again going to decrease. So we know that the density of water is directly related to the temperature of this water, right? And we are interested in predicting the temperature of the water. The other interesting fact we know about density is that on the right is that as you go deeper into the lake, the density of water always monotonically increases. And that's because of water pressure, right? As you go deeper into the layer, you would have more layers of water columns which are applying more pressure, and thus the density increases. So that's like an intuitive explanation, kind of. So the constraint we know is that as you go deeper into the lake, the density of water is always going to increase. And by knowing this density, we are able to go back to temperature, right? We can predict temperature. So here I'm showing this schematic where, as you see, as you go deeper into the lake, the density should always increase. So in this talk, I'll refer to this as like the physically consistent temperature profile. And say in certain regions, if the density goes below, like say if the density does not increase in our predictions and decreases actually, then we'll say that is like a physical inconsistency, right, in the model. So, and we want to avoid these physical inconsistencies. Uh, so, uh, so let me introduce the concept of this physics-guided learning paradigm, right? So the physics supervision, which we know this, for example, this density constraint or this monotonicity constraint, can be very easily enforced as like a soft constraint, right? So along with minimizing your empirical error, which is say usually your mean square error, or some other say negative log likelihood or any form of empirical error you have, you can simply add this physics loss term to it with some hyperparameter lambda, and then you can minimize this combined objective together, right? So technically you are minimizing your empirical error plus the physics loss term. So this is similar to enforcing this as like a soft constraint where the model would be penalized if any of these constraints are violated at any point of time, right? The advantages of this formulation is that it's very easy to use. As you can see, any form of constraint, say if it's in the form of a closed form equation or a partial differential equation or any other form of constraint can be very easily incorporated into the training. So that's one of the most standard ways of doing physics informed machine learning. The other advantage is that it's also unsupervised in most cases, which means that you don't really need labels for your physics loss term. In case of say temperature, you don't really need to know what the exact temperature values was. You can basically just apply this physics loss on an unlabeled data set, which is really useful. So you can train your model in a semi-supervised fashion. The disadvantages are that this constraint is not always satisfied during testing or evaluation, right? You are just applying and forcing this constraint as a soft constraint on your training set. But while testing, you do not have any guarantees that this constraint would always be satisfied. The other disadvantage is that this formulation is also sensitive to small perturbations in your model weights, like if your neural networks It's very sensitive to these neural network model weights. If you make small perturbations, the predictions are no longer physically consistent. And we'll come to this point later on in our talk, where we'll show. So this may not be very intuitive right now about why that is true. So we'll talk about this later. So one of the ways to do uncertainty quantification is with this Monte Carlo dropout. So there is this paper about dropout as a Bayesian approximation, and that lets us do uncertainty quantification while using this dropout, right? So in deep learning, Monte Carlo dropouts were originally introduced to prevent the model from overfitting. And what that means is that like we can just use dropouts. So the main idea is that you can drop out, say if you have a neural network, say a simple fully connected neural networks, you can drop out random neurons while training, and then that would prevent the model from learning some co-adaptations between neurons. So that essentially helps the model prevent overfitting, right, to a particular training set. So that was the original motivation, or originally how dropouts were introduced. But then this paper also provided a theoretical way which showed that if you want to use dropouts during testing or evaluation, you can actually achieve, you can actually perform uncertainty quantification and get a distribution on your output space, right? And how that is done is, so say you have a trained neural network, which is shown on the left. You can just randomly drop out, say, P% of the neurons, and you would get some different model, right? Some different connectivity in the model. You would get a different output. You can apply dropout once again. You'll get a different set of neurons would be dropped out. Say, for example, this one, and you would get a different output, right? And you can combine all of these different. You can repeat this thing n different times and get n different outputs, and then you can just combine all of these different outputs to get your desired distribution, right? So this paper showed that this is equivalent to learning a Bayesian neural network, which was also known to do uncertainty quantification, right? And this is much faster than other methods of doing uncertainty quantification, and it's really easy to use, right? So we try to focus on how can we do uncertainty quantification with Monte Carlo dropouts. So how do we extend this to physics-based loss function is the next question, right? The very simple way is like we said, right? So while training with your empirical error, just simply add this physics loss function to training this neural network, and the job is done, right? So we would perhaps we would have a trained model on the physics-based loss function, as well as we would have a way to do uncertainty quantification, right? So that should essentially work, right? But what we saw was that it doesn't. And what happens is that if you train this entire neural network with this loss function, the physics, even if you properly train it, say the physics assumptions are satisfied while predicting, what we saw was that once you apply this Monte Carlo dropout, right? Once you randomly delete certain neurons and try to get an output and then combine all of them to get a distribution, we saw that suddenly these predictions are no longer physically consistent, right? Even though the original model was physically consistent while predicting, by randomly dropping out neurons, we have broken this, whatever the neural network has learned, and it does not really predict physically consistent solutions anymore, right? So these trained models, although they were physically consistent, the predictions are no longer physically consistent. So that's a real problem, right? So the next question is, how do we overcome that, right? So the line of thought for this process was, can we somehow, since we have like a very simple monotonicity constraint at hand, can we somehow hard constrain the architecture, right? So can we somehow build a different architecture which would always satisfy these physics constraints, right? And the main idea was to build a architecture which is not sensitive to these small perturbations, right? So if you drop out certain neurons and certain connections, can we build a network which is not sensitive to these small perturbations? And that would be useful because we want to do uncertainty quantification with dropouts, right? If it's not sensitive, then probably we would have uh, a meaningful uncertainty estimate, right? So that was the primary goal of designing a specific architecture. And what we proposed was, So specifically for this lake temperature modeling problem, what we proposed was, so as I was describing, the goal is to predict the temperature of the water along depth as well as along time, right? So there is two sequences. One is the sequence along time. The other one would be a sequence along depth, right? So to handle the sequence along time, we had like a temporal autoencoder, which can learn some time-dependent features, right? And those features were passed into a monotonicity preserving LSTM, which would, so we would take in our inputs and we would predict the density, right? Since we know that the density is always monotonically increasing, can we predict this monotonically increasing densities, right? And from this densities which are physically consistent, if I may say, we want to get back the temperatures, right? So it's twofold. We want to predict densities which are not violating these physics constraints. And from these densities, we want to predict back the temperature, right? So, this is the overall framework, but let us look at each individual component separately, right? So the first one is extracting some temporal features, right? So as we know, say, for example, if you want to predict the water temperature, or say, for example, air temperature today, we know that the temperature today is highly going to depend on yesterday's temperature, right? And so on and so forth, right? So we need to somehow model this temporal dependencies of temperature, right? So what we did is that, say, for example, we took our input time series, say the temperature of water for the past 7 days, and we wanted to learn a latent representation Z from which we can decode back the entire time sequence, right? Say if we know the last 7 days of temperature, we learn a latent representation from which we can reconstruct back the entire time series, right? That means that this latent representation would actually contain the information about how this time series varied across the last 7 days, right? So that's how we got this time dependent embedding, which we would use later in our model, right? So we would be using the time series temporal embedding into this monotonicity preserving LSTM, right? So this LSTM is like a machine learning model or a deep learning model, which is useful for predicting sequence, right? So we use that to predict the density estimates. So this is the architecture of the monotonicity preserving LSTM. Like the components in red are the novel physics informed innovations which we did to enforce this monotonicity constraint. So usually the LSTM has its own forget gates, input gates, and some other output gates and stuff like that, which helps it learn these sequences better, right? So it has some sort of a memory which can help it predict the next output in the sequence better, right? So what we did to that was we simply took the output of this LSTM, whatever it used to output, we passed it through some fully connected or dense layers and predicted some quantity, and we passed it through a ReLU activation, right? So ReLU activation is like 0 for negative outputs, and then you have positive y equal to x for the positive output. So it ensures that whatever you get is always positive, right? So once passed through this ReLU activation, we get delta D, which is always positive. And then we simply add it to the Z of D, which is from the previous time step, right? Or previous depth sequence. And by adding this output, we are able to ensure that ZD is always greater than or equal to the previous state output, right? So we ensure that delta D is always greater than or equal to 0. So that's how we were able to enforce this very simple monotonicity constraint. And by doing that, we were able to predict density, which is always increasing with depth, right? And that did have a significant impact on the predictive performance. So we have this physics guided architecture, right? So we hard coded this physics constraint, this monotonicity constraint into our LSTM, and we were able to show that for 2 different lakes, we were able to achieve much better performance, as well as we were always able to achieve like 0 physics inconsistency, right? Whereas the other solutions, they weren't physically consistent so much, right? And we were also able to show that for different training fractions, even how small of the data you use, we were always able to get much better results than a standard LSTM or the LSTM trained with like the loss function. And we like yeah. So so the next thing was visualizing this temperature profiles, right? We wanted to see like where we are actually improving, right? So these are three representative dates, like from which we are predicting the temperature profiles. And if you look at the LSTM, the physics guided loss function of the LSTMs, as well as the architecture, like all of them looks like decent predictions, right? And you may not see that why one may be better than the other than improving on the RMSE, on the predictive performance, right? So what are we actually gaining out of this? Like all of these distributions look pretty valid to me, although the architecture may be slightly better because the distributions are much wider and they cover like a greater 95% confidence interval. But still, I think all of them look good. But once we try to look at individual profiles, right? So remember that each of these distributions, how we plotted them was we ran this models 100 different Monte Carlo. We took 100 different Monte Carlo samples for each of these models, and then we averaged them out, right? So we computed the mean and the standard deviations, and then we plotted like the predictive interval from these 100 different Monte Carlo samples, right? But if we actually look at each of these individual Monte Carlo samples, we can see that even though the average distribution looks good, each of these individual predictions are not physically consistent, right? So each of them are very haphazard or random, right? Even that's probably expected for the LSTM, where we don't know the physics constraint, where we haven't used the physics knowledge at all. But even for the one which was trained with the physics laws, right, which was supposed to do much better, we still see that each of the individual predictions are not physically consistent, right? They are all over the place. And that is where I talked about that these models are very sensitive to these small perturbations in the model weights, right? But on the other hand, for this physics guided architecture, we saw that these predictions are much smoother, right? So since we hard coded this physics problem, we were always able to get good results on your output, right? And that significantly improved the performance. Before we go to the next section where we talk about a general case of physics knowledge, I want to ask if you have any questions. Maybe a brief 5-minute questions would be good.
So if there are any questions, you can type it, either ask it in person or type it in the chat box. David, you have a question? Okay, go for it.
Yeah, I do. I was wondering actually. So how are you applying the uncertainty quantification here? So you completely you're not using dropout anymore in this?
No, I'm still using dropout, right? So
Okay.
the thing is, I'm still using dropout, but now instead of the simple LSTM, I have this physics informed LSTM, right? This architecture change.
Okay.
So even if you randomly drop out neurons in, say, the LSTM architecture or the dense layers, the density would still always be monotonically increasing, right? Because we have this hard-coded constraint which would help us predict a density which is always greater than or equal to the density in the previous depth step, right? So that's why no matter what many neurons you drop out, the density would always increase with respect to depth. And that's why this model is not sensitive to these small perturbations.
Okay.
Tom,
Go ahead.
Hi, I have a question about the dropout. Would
Yeah,
you mind
please.
bringing it back to the slide where you showed yeah, that one.
Mhm.
Sorry, the one with the I think it was the one after with yeah, this one. So it looks like here you're training with the full neural network without dropout on using the
No,
physics
we are
loss
still training with
functions.
dropout. We are still training with dropout.
Oh, okay. Sorry. I just saw it looked like you were training without dropout and then applying the dropout only for the predictions.
No, I think so. While training, I think dropout usually acts like a regularization, right? But then while predicting, we are still using dropouts
Okay.
to predict the outputs, right?
So you have dropout for both training and
Yes.
but okay, cool.
Yes. So usually the practice is when you are using dropouts for regularization, usually the practice is you just use it for training. And then once you're testing, you don't really use dropouts, right? So you use the entire neural network architecture. So here, for if you want to get an uncertainty estimates, you usually use dropouts for both training and testing, and then do some sort of a scaling in the end. Any other questions before we move into the next part of this talk? We can come back to the
So
question.
just a quick one then. So if dropout is used on both the training and the evaluation, why is it that you think the results stop becoming physically consistent?
Yeah, that's a very good question, actually. So although I think so, it seems like even though we are using dropouts on training and testing, it seems like the model just learns to enforce this physics consistencies on the expected value, right? On the mean. So it tries mostly to make sure that the means the means respect this physics consistency distribution. But once you look at each of these individual predictions, it no longer satisfies these predictions. I think that's what we observed empirically, at least. But I think that's a very good question, which we don't have like a lot of explanation for.
Thanks very much.
Right. Okay. So we have another question from Paul. It's best, I guess, if we'll take this last question and perhaps move on.
Okay. Yeah. Maybe one last question and then we'll move to the
Paul, go ahead.
Hi. So just following on from that last point, when you do the dropouts in training and then in testing, is it completely random independently both times, or could you actually use the same sort of pattern of dropouts when you like 100 different dropout realizations that are the same in both training and testing to ensure that the physics is maintained?
No, I think so. So I think the dropouts are randomly applied, right? So at training, like it's not that we have a fixed set of dropped out new neurons, right? So I think dropout usually follows like a Bernoulli distribution with a certain probability. So you usually define, so for this work, say we defined, will randomly drop out 20% of the neurons. So while training for each of these, each of the training loops, right? For each of the different batches, it just randomly drops out 20% of the neurons from a Bernoulli distribution. And then during the next iteration, it randomly drops out another set of 20 iterations, right? 20% of the neurons. So they are at random. So we don't have any control about.
So you couldn't actually recover anything meaningful.
Yes.
Subsequently in the testing. Okay.
Yes. So that may be one of the reasons why we see this perturbations, right? Yeah.
Okay.
Thank you.
Okay.
Thanks, Paul. So we'll, if anyone else has any further questions, if you don't mind, we can ask them maybe towards
Yes.
the question.
That would be good.
Okay, go ahead.
So the next part of this talk is going to we are going to talk about uncertainty quantification for a general case where we don't, say, for example, don't know the form of this physics knowledge, right? How can we do uncertainty quantification then, right? So that may be a more challenging problem. So formally defining uncertainty quantification again. So we would try to approximate a posterior distribution of your output, say probability of your output y, given your inputs x, as well as some latent variable z, right? So usually a latent variable model is formulated in a way that your inputs are deterministic, say x, and you also have a latent variable z, say some noise distribution, or some other distribution where you know z is sampled from a prior distribution. And what we are interested in this posterior distribution of your outputs, right? P of y given x and z, right? So that's the formal definition of uncertainty quantification. And also, say if we have some k different physics constraints, we would be interested to make sure that our predictions satisfy these k different constraints, right? So that's the general problem setup. And the background on pins is that like pins were originally developed to solve nonlinear partial differential equations. So we usually formulate the output of this solution of this prediction, of the solution of this PDE or partial differential equation as a neural network. And then using automatic differentiation, we can compute the gradients, right? Say du, dx, all of the gradients which are there in the partial differential equation. And you can make sure that these predictions enforce the partial differential equations. You can also have like the mean squared loss, the empirical error, which we showed later on. you can have this loss term on your initial and the boundary conditions. So in that way, you can enforce you can train your neural network to predict the solution of a partial differential equation. Again, the same thing, pins have a problem with dropout, right? So the trained models can be physically consistent, but these after perturbations, we usually see that the predictions are no longer physically consistent. And the other thing which we see for a general case of physics loss functions is that there may be multiple terms, right? For example, we have 2 terms, or there can be 4 terms, 5 terms, and there may be an imbalance in the gradients for these different terms, right? So one of these terms can start training, say, for example, the network can start training on this mean squared loss term and completely ignore the other loss terms if the gradient are imbalanced, which can happen in a general case. So we want to avoid that scenario, right? Where the imbalance in the gradients can affect training. So the next baseline which we wanted to do uncertainty quantification in a general setup was this conditional GANs. So I think probably you're familiar with that GANs have been used for this generative. It's one of the generative models which can generate, I think, realistic faces, images and stuff like that, right? And can do like, say, image to image translation and can do a lot of generative modeling stuff, right? But I think people also recently tried to do uncertainty quantification with GANs and use them as like latent variable models such as like variation autoencoders and stuff like that. So the main idea is the generator, you take in your input X and Z, the noise variable, and try to predict your output Y. And there is a different model, the discriminator, which tries to distinguish between real and fake examples, right? So if you input the ground truth example, like say X, and your ground truth prediction Y, the discriminator would try to say it's a real example. But if it's a generated sample, then it would try to say it's a fake sample, right? So if we look at the loss functions, the generator loss function is simply trying to minimize the discriminator scores, right? So 0 means it's a real sample. So it's trying to fool the discriminator into thinking that this prediction was real. But on the other hand, the discriminator is simply like a binary classifier trying to classify between real and fake examples, right? So this is like a cross entropy. So this is like a simple cross entropy loss function, right? So that's basically the adversarial chaining which happens in a standard conditional GAN. So the problem is we don't consider the physics constraints here, and we also don't make use of this unlabeled data, right? So usually this physics informed machine learning is done in the form of this semi-supervised learning, where you have a set of labeled set and a set of unlabeled set. Usually the unlabeled set is much more larger than the labeled set, right? So this standard formulation does not take into account the unlabeled set, right? So the simple extension is, of course, to the generator, you can add this physics loss function, which would say, okay, while predicting whatever you are predicting, right, the output variable Y, why not make sure that your predictions also satisfy this physics knowledge, right? Also satisfy this physics equation. So that's like a very simple way, right? Similar to how you would do it for pins, right? Or even previously how we did it, right? Simply add it to the generator, right? But there are problems again. So first of all, the discriminator here does not take into account the unlabeled data. So it's not using this large amount of unlabeled data. It can also suffer from this imbalance in gradients, right? So as you might, if you have trained GAN slightly, you'd know that training GAN is really painful, right? Like it has a lot of nuances and it's not really very stable, right? This adversarial learning which happens, I think there are lots of things like mode collapse can happen and has a lot of problems, right? So if you add a gradient imbalance problem on top of that, it becomes really difficult to train GANs, right? So it basically, in summary, it basically fails to exploit this adversarial learning framework. So the question is, how can we formulate it better, right? So the main idea here was, can we use this physics supervision to train both the generator and the discriminator, right? Can we somehow help the discriminator from this physics knowledge? Can we also use this unlabeled data to train both the generator and the discriminator? And can we somehow prevent this gradient imbalance, right? Which is which makes training GANs much more difficult, right? So can we do something about that, right? So the motivating question is, how do we actually introduce the concept of physics inconsistency in the discriminator? And we actually came up with a very simple method to use this physics consistency for the discriminator. So what does the discriminator actually do, right? So the discriminator takes in your inputs X and whatever you have predicted Y, and it tries to predict that it's a fake example, right? And for a ground truth example, it tries to say it's a real example, right? So it tries to distinguish between what's a real example and what's actually generated by the generator, right? So it tries to distinguish between those two. So now what we are doing is that we are simply adding this vector eta, which we are calling as this physics consistency score vector, and that's basically simply like a probability, which is e to the power minus the physics constraint what we had, right? So if your physics if your constraint is satisfied, then your residual becomes 0 and this eta becomes 1, right? So it means that it's always physically consistent, right? So the probability of being physics consistent is very large, right? But if you have a large residual, this eta would very fast go to 0, right? Which means your predictions are not physically consistent, right? And by adding this, the motivation is, can we help the discriminator by adding this physics knowledge, which it can use to distinguish between the real and the fake examples, right? So if it was a real examples, the physics predictions would always be 1, right? The vector would always be 1. But if it's not 1, then the discriminator would think that, okay, the physics consistency vector is not 1, which means it's highly likely that it's going to be a fake sample. So we can simply add that, right? So the generator loss function would have two components, one on the labeled data and one on the unlabeled data. And again, the discriminator loss functions would again have two components. So you would have two different binary cross entropy losses. One would be on the labeled data, which is the fake examples, and one would be on the unlabeled data, right? So you must note that this physics consistency vector for the real samples are 1, right? So it's always equal to 1. So it means that the physics constraints are always satisfied. So that's how we create this physics informed discriminator, PID-GAN. And we theoretically show in our paper that we do not suffer from this imbalance in gradient dynamics, right? And then I think we also try to extend our work to imperfect physics. By that we mean, say for example, in certain applications, we don't really know that these physics principles which is available to us are correct or not, right? Say for example, these physics principles are sometimes derived using simplistic assumptions of these complex real world phenomena, right? For example, if you are trying to predict what is the velocity of the two particles after collision, and if you're assuming that momentum and energy is conserved, it's probably not always true, right? These collisions are not always elastic collisions, and there may be some loss of energy and loss of momentum, right? So these, if you try to ensure that these physics constraints are always satisfied, that may not be always correct, right? So these residuals may not always be equal to 0. So how does the model perform in certain situations where these physics knowledge are not always correct, right? Are you misleading the model by applying these constraints? So we actually extended our work to that scenario as well. For the time being, I'll skip that discussion. But we do have a method to do that. Feel free to read the paper if you're interested in this thing. So the two case studies we performed was, the first one was solving this partial differential equations. So we took three different equations, the Burger's equations, the Schrodinger equation, and a 2D Darcy flow equation, and we tried to predict the solution of this PDE from these equations, right? So on the Burger's equation, so the different baselines we tried simple PINNs with dropout. There is an adaptive version of PINNs which actually tries to balance the different gradient terms. We tried to add dropout to it and see how does that perform. Then we had this physics informed GAN loss, which is adding the loss function to it. And then we had this physics informed discriminator, right? Which is our method. And we saw that our method actually does better on the error, on the residuals, as well as on the 95% confidence intervals for both noisy and noise-free settings, for all of the equations, for Schrodinger's equation as well, and as well as our Darcy's equation. So all around the board, we were able to outperform the other methods by a significant margin. And then I think the more interesting part is this physics-informed GAN, which did not perform so well. We actually tried to look at these individual gradients, right, for each individual layers. And we saw that these gradients were imbalanced, right? You can see that this gradient at the layer 5 of this neural network, one of the gradient for this loss terms was much larger than the other gradient, right? So that would drive the model to learn this one loss function more over the other, which would make the training of the scans even more imbalanced, right? But for our case, we show that our formulation actually by design, it always has balanced gradients, right? And we show this across all of these different examples like Burger's equation, Schrodinger's equation, and the Darcy flow, right? We show this, our method always has balanced gradients, but for the other method, it may or may not have imbalanced gradients, right? So the next case study was on this real world simulations, right? So the one I was talking about. Say if you want to predict the velocity of two particles after collision, and say if we know that there is this friction on the surface, then even if we try to conserve momentum and energy, that may not be the best thing, right? Depending upon the amount of friction you have, there may be violations on these physics constraints. Also, we had another problem, which is tossing trajectory predictions. Say if we are tossing a ball away, we want to predict the trajectory of this ball, but we know that this force is applied in this downward by this gravity. But there may be other forces which we are not observing, right? Say a random wind may be there, which might deviate this ball or this particle, and that may lead to this physics violations, right? So the simple kinematics equations might not hold. And we again compared with the same baselines. And the interesting fact to note was the standard conditional GAN actually performs better than this physics informed GAN, right? This loss function type of GAN. Although our method performed much better than both of these baselines. And the reason that PID-GAN did not work well was because we were simply forcing the model to learn to learn this physics constraint, right? Which may be incorrect, right? By forcing the model to satisfy this energy constraint, say, that may be misleading because the energy constraint is not actually getting satisfied on your real predictions, right? There is a violation of this physics laws that actually made PID-GAN perform worse than the conditional GAN. And we were also able to show on different training fractions that we were able to perform much better. But let me show another interesting phenomena, which is so we were adding this physics consistency score, right? Onto the discriminator, right? And the discriminator was using this physics knowledge to distinguish between real and fake examples, right? But if you try to plot the physics consistency score on your real ground truth data, right? So usually you would expect, say, on the partial differential equations, the ground truth examples would always have a physics consistency score of 1, right? It would mean that they are always physically consistent, right? But for these data sets where the physics equations are not always satisfied, the score is not always 1 on the ground truth examples, right? So they are varying from 0.8 to 1. But if you look at the blue line, which is the physics consistency score on your physics informed GAN, so it's trying to make them very close to 1, right? So which is incorrect, right? It is not following the distribution of your ground truth examples. But for our PID-GAN, like both on the labeled and the unlabeled set, it follows a ground truth distribution, right? It does not try to maximize the physics score to be 1, right? But the physics informed GAN, it just blindly tries to make the score to be close to 1, and which actually impacts the model performance, right? So it's trying to make sure that this energy conservation is always satisfied, but by actually forcing the model to satisfy the energy constraint, it's actually doing much worse than what it should do. So by actually following the ground truth distributions, our model was able to perform much better rather than blindly trying to follow this physics law, which may be incorrect, right? That brings us to the end of this talk. Any questions from the first part or from the second part?
Thank you very, very much, Arka. It was very comprehensive. So we have a few minutes, 8 minutes for questions. If anyone has any questions, feel free to ask away. I just have an overall sort of question, mostly about interpretability. So I find that one of the advantages of incorporating physics in this sort of learning frameworks is that you can also work towards interpretability of the dynamics, perhaps in this case. So, but I find that these loss function-oriented approaches kind of suffer from that, because in the end, the training does not give you any view into the interpretability of the dynamics. In the case, for example, of the lake, can you comment about this, perhaps?
So I think for the lake, I would say it's still much more interpretable than this the physics informed discriminator one. It's because I think for the lake, we try to predict like an intermediate quantity. Say, for example, here, we try to predict the density, and we know that so we can either model directly from the input to the output, right? So we can take in our input drivers and we can directly predict the temperature profile. But what we are trying to do here is that we are trying to predict an intermediate variable, say density, where we know that this physics principle holds. And then we are trying to, so we are decoupling this entire box into, say, smaller components, and we are trying to enforce this physics consistency on each one of them. And we are predicting a density which always satisfies this physics consistency. So it's still somewhat interpretable. It's still predicting these density estimates without actually observing the densities of the water directly, which makes it better than these other models. But coming back to your question, I still agree with you that I think in the future a lot more work needs to go into to make this more interpretable, because still each of these individual modules, right, which are going from your input drivers to density, or say from going from density to temperature, each of these individual modules are still black box at nature, right? So they are, even though they are trained with this architectural changes or stuff like that, they're still very black boxy in nature.
Yeah.
So it's still not as
true.
interpretable as we want it to be, right?
Correct.
As
So,
like say a physics-based model, which we would know how we convert this shortwave radiation to compute some energy, and from this energy we try to compute density, right, and so on. So these process-based models may be much more interpretable, right? So we are trying to, so in a recent work, we are trying to actually create surrogates where we would replace each of these process-based models by small machine learning models, which would make it more accurate, but at the same time it would make it more interpretable. So that's some of the recent works I've been trying to do on say extending these frameworks. But
and
still at scale, it's not interpretable.
Yeah, and if I may to add something else, is so even in terms of generalization, do you have a criterion that tells you know how close you are or how well you are discovering the governing dynamics? So I guess on this note, how well has this model generalized for different starting conditions?
Yeah, so I think what we did was that we trained on a different time period. Say we trained, I think, from what I remember, we trained from 2017, so 2013 to 2018, and then we tested on a completely new set of years, say 2018 to 2020, and we found that our model actually generalizes pretty well on future dates, right? So by actually enforcing these constraints, by density constraint, you are actually able to get a decent generalization performance as compared to other black box models. But discovering governing equations, I think, is a completely different topic, perhaps. Here, I think we assume that we know these governing equations, so we did not try to get back the governing equations, right? But I think that's also one of the different works. I think there are papers like Cindy, which try to
Yes, I
discover
mean,
governing
yeah, I
equations
don't
from
intend
data.
to discover the governing equation, but sort of how close you are towards, you know, a governing model.
Yeah, I think we performed much better. Like we also compared to these process-based models, which were mostly physics models. And in terms of RMSE predictive performance, I think we were much better. We can predict the temperature of the water by better than 2 degrees Celsius. So we had a lower RMSE, much lower than these physics-based models. And probably that goes back to this black box nature of neural networks, which can fit any arbitrary function, right?
Yeah.
Much better. Yeah, but still, I think interpretability is still somewhat lacking, in my opinion.
Okay, thank you so much, Arka. So, do we have any questions? We have a question.
Thanks for the great talk. How would you calibrate your uncertainty obtained from using your Monte Carlo dropout method to some sort of real world uncertainty on the prediction? So maybe some sort of likelihood of prediction.
Can you repeat that question? Sorry.
Yeah. So if I understand correctly, is the Monte Carlo dropout some a sort of proxy for network stability, as it were, how stable the predictions are for the neural network? So how would you present, how would you calibrate that to some sort of, given these set of inputs, what is the percentage likelihood of an output?
Okay, so I think so. So this paper, which actually did this, which proposed Monte Carlo dropout, I think they showed that this method is somewhat stable to the choice of this percentage of neurons you want to drop out. You can usually drop out anywhere from 20% to 50% of the neurons, and the model actually predicts the entire confidence interval properly. And so usually the other method is, so an alternative to do uncertainty quantification without dropout would be Bayesian neural networks, which assume that, say, each of these layers weights, we usually assume the layers weights are just one matrix, right? But the Bayesian neural network usually assumes that these weight matrices have like a both mean and a standard deviation. And while doing this training, you can actually sample from this. So each of these neural network weights would have a distribution, right? So you can sample from these distributions of weights and you can get a different output, right? So that is the Bayesian neural network way of doing uncertainty quantification. But the problem with Bayesian neural networks is that it's very difficult to train. Like you have twice the number of parameters, so it's much more slower and has a lot of other problems while training. So I think this paper, this Monte Carlo dropout, they were able to show that that they were able to achieve same performances, and they also theoretically showed that it's equivalent to a Bayesian neural network by doing this sampling. So I think it has all of the same, so it shares all of the same theoretical properties which a Bayesian neural network does.
Thank you.
But in practice, though, I should say that this method has some problems, which I think recent papers in 2021 or something have shown that Monte Carlo dropouts are somewhat sensitive to the choice of probability you pick and stuff, and some other shortcomings. Did that answer your question, or perhaps not?
No, that's lovely. Thanks.
Okay, thank you.
Okay, David.
Yeah, thank you, Arka, for this presentation. I still have the feeling that there was someone who raised a hand on the first part. If I am correct, please feel free to raise a hand again. But I have a question. So on the second part, you are using the GAN, yeah, fitting
Yeah.
GAN effectively. So you are, if I'm not wrong, you abandon the dropout method.
Yes. So for a general case, I think we have a baseline here that we try to use place-informed pins with dropouts, right? And from our previous research also, we know so pins with dropout do not work very well, right? So that's why we abandon this dropout methods for a general case, right? So if you can still create an architecture which is not sensitive to these small perturbations, dropouts would work. But for a general case, it's very difficult to say if you have a partial differential equation, right, which is say complex as like Schrodinger's equation or something. It's very difficult to come up with an architecture which would always satisfy the Schrodinger's equation, right? And for every different problem, you would need to come up with a different architecture, right? Even if you can come up with an architecture for a certain problem, it's going to be difficult to come up for a general set of problems, right? So that's why we try to go to this GAN approach, where you can still use this discriminator to ensure your predictions are still satisfied while ensuring these predictions are again physically consistent, right? So that's the motivation we had from going from dropouts to GANs.
So you mean that this kind of approach works in general better than the dropout approach? Consequently, does that mean, or will they be for the different applications or?
Yes. So for the dropout approach, since we have the physics knowledge hard encoded, the residuals would be zero, actually equal to zero, right? Always, because the architecture is hard coded, right? To create this physically consistent predictions, right? But for this PID-GAN, again, this GAN approach, you're still again just doing somewhat better than the soft constraint, but again, it's still a soft constraint, right? So you would have these small errors in your predictions, right? So these physics constraints are not always going to be fully satisfied. You would still have a small, though yet non-zero approximation error and physics error. So I think it's a trade-off. Like if you can design an architecture, perhaps it's going to be better to design an architecture to enforce that law, but which is usually much more difficult for complex physics problems. So this GAN approach works better in general. Like if you don't want to create an architecture which works well for your problem.
All right. Okay, I think we'll call it a day here. And unfortunately, I need to vacate the room I'm in. Thank you all so much for joining. Thanks again, Arka, for sharing your work, and best of luck with the rest of your PhD.
Yeah, thank you so much for inviting me. It was really amazing.
It's a pleasure. So again, thanks to everyone for joining, and stay tuned for our next seminar. Have a good day, everyone.
Thank you, everyone.
Thank you.
And thanks, Arka, especially.